we have Abacus CAE, which is a complete Abacus environment, but also helps users to build models right from scratch. If you're not going to import your models from third-party tools, you can as well build the models in Abacus CAE. And then you have fracture and failure capabilities, which will help you to simulate steady, the fracture mechanics kind of problems. And then you have direct cyclic analysis, which I'll get to it in a short while. It's basically it's an analysis carried out to find out the stabilized response of a structure. So talking a little bit in detail about what are the different kinds of analysis that one may have to do in this kind of an industry. One is, quite often we come across coupled thermal mechanical simulations being simulated. So in the next few slides, I'm going to talk about the different kinds of analysis one may have to do to capture some of the effects that we have been discussing, like fatigue, creep, thermal mechanical. And you'll also see some case studies from customers wherein they have been doing this kind of a work, and they have presented many papers in different conferences. So if you talk about coupled thermal mechanical simulation, so it's an analysis wherein you have the thermal field and the mechanical field interacting with each other. So one field is dependent on the other. And one typical application is to kind of analyze the lead-free solders if they're undergoing like thermal loading on and on. Now, it's quite common that electronic components are subjected to several cycles of thermal loading, and because of the various coefficient of thermal expansions that the materials has got, they'll kind of induce stresses, and the stresses are so high that they can cause plasticity or creep in the structure. And solders are at risk because they tend to stress at temperatures above their boiling point, and at such stresses, they kind of undergo plasticity and creep, and due to this repeated kind of loading, eventually the product tends to fail. So it becomes very important that we study the thermal mechanical behavior and the long-term response by doing coupled field analysis such as thermal mechanical. And then the other thing is thermal electrical. Like for example, in this picture that you are seeing, if you see the diode, so if there is too much current in the diode, it causes Joule heating, because of which the solder tends to melt. So if you want to capture this kind of a response, you could as well do a thermal electrical simulation. And this is a slide showing you the contours. So you can see here the contours of temperatures being shown when you do a thermal electrical analysis. Now, you could also have a case wherein you have all the three fields interacting with each other, that is thermal, electrical, and stress field. So you can also do you can also do this kind of analysis wherein you have multiple fields interacting with each other. So this is a typical example of a spot weld wherein you have electrodes, kind of doing spot welds on a sheet of metals. So you can see the temperature distribution, the potential, and the stress field. And then we can also perform electromagnetics, wherein we can simulate the low frequency eddy current analysis, which is nothing but the induction coil kind of analysis, wherein you place a workspace in a time varying alternating magnetic field, which will then cause heating in the workpiece. And then many times electronic components are subjected to vibration and shock. So Abacus has got very powerful solvers for simulating these kind of analysis. That is, it has got many linear dynamic procedures like steady state analysis, random response, model dynamics, frequency extraction, which is the base for all the model dynamic procedures. So it has extensive linear dynamic capabilities, and you have very good performance. You have very good solvers, high performance solvers, and you could do a frequency dependent or a time dependent kind of analysis. And then you have the thermal cycling. So thermal cycling is where you have like multiple thermal loads being applied in repetitive cycles. So one way to do that is to actually simulate the structure for so many cycles of load, which is going to be computationally expensive. So you might have to do some repeat of, say, some 100 cycles or 200 cycles, then study the response of the structure, and then further take it down to some fatigue analysis. So to avoid such costly, expensive calculations, there is a procedure in abacus called the direct cyclic procedure, which can be used for calculating the stabilized response of the structure. So abacus automatically computes what is the stabilized structure, what is the stabilized response, after how many number of cycles the structure is going to reach to a stabilized state, and from there on one can carry out the fatigue analysis. So this is a quick example of how a direct cyclic method was used for solder joint reliability analysis. So solder joint failure is a common thing in electronics industry. So one can use the direct cyclic procedure to get to the stabilized response, and then further upon it apply thermal loading or mechanical loading to simulate the failure of the structure. So as you can see from this example, so using a manual approach, one had to use, to simulate the failure of this particular solder joint, by following a manual approach, one had to use 8 cycles, follow so many number of increments, iterations, and then this is the CPU time. Whereas by using the direct cyclic procedure, one can cut down all of these things, that is the runtime can be drastically reduced, and the number of increments and iterations needed are also way too less. So the direct cyclic procedure basically helps the user to get to a stabilized stress strain response, which will then act as a basis for thermal loading or mechanical loading. And then there are things like moisture sensitivity analysis, warpage, which can be also simulated. So basically, for doing this moisture sensitivity analysis, one can define material properties as a function of predefined variables. Temperature, for example, is a predefined variable. So we can define material properties as a function of temperature. So likewise, we can have material properties varying as a function of moisture or some radiation, and then do different kinds of analysis. And then, like as I've said, one can use the CFD tool for doing cooling kind of analysis, wherein you can solve heat transfer kind of problems or a sequential thermal stress. You can simulate natural or forced convection. So basically to see what is the cooling effect or the heating effect. And one other important thing is on fracture and failure modeling. So there are like different methods and techniques available in abacus for solving fracture and failure. So if you look at the classical fracture mechanics tools, so you have a crack defined, and then you see what is, you kind of have a very defined mesh at that area, and then you see the J integrals, stress intensity factors, and etc. And then we have some special purpose elements called the cohesive elements, which basically can be used for studying delamination or debonding kind of problems at the interfaces. So if you want to see the peel-off kind of studies, you can use cohesive elements. And then we have a very advanced technique called as the extended finite element method, which can be used for simulating, again, crack growth and propagation. So here, it's not necessary that one needs to specify an initial crack path. So it's kind of mesh independent. So your mesh could start anywhere in your model. It could be across elements. It's not necessary that the crack path follows the element. And then you can also simulate wear modeling and then bulk material failure. So here is an example wherein XFIM was used to estimate the probability of crack propagation in stacked IC package. So basically, by doing these kind of analysis, designers also can get ideas as to what could be altered in the design iterations to avoid such kind of a failure. And then wear modeling. So wear modeling is nothing but removal of material, ablation, wear. So we have techniques which can be used for modeling things like wear. So the technique which abacus uses for modeling wear, that is removal of material, is adaptive arbitrary Lagrangian Eulerian method, wherein remeshing is kind of involved, and it kind of does mapping. So this is done without changing the element topology. That is, having the same number of nodes and elements, the mesh is kind of altered in such a way that users tend to see some amount of material removal. So in the picture that you are seeing, So you can see this is a fluid velocity dependent wear of a well bore, wherein this was the initial, the right hand side is the initial configuration, and the final configuration you can see that there is some kind of material which is eroded. And then wear modeling, this is, it's also kind of quite typical in electronic applications that when the components are subjected to shock or vibration and for several number of cycles, you tend to see some amount of wear being caused due to the contact between the different elements, okay, like the connectors and things. So one can create a representative finite element model and then simulate for number of cycles. So apply a load and then simulate the vibration effects, and then repeat the loading for different kinds of different cycles, and then see what is the wear caused by, say, contact. So in this example that you're seeing, the simulation was run for over 2,000 fretting cycles, where wear was occurring at the contact surface of the connector. So the contact pressure distribution that you see at the interface, that is where there was excessive contact pressure, and due to the vibration of the structure, wear was happening. And then low cycle fatigue. So in abacus, one can perform low cycle fatigue analysis, wherein it's an extension of a direct cyclic procedure. So without having to use other tools for modeling fatigue, one can perform low cycle fatigue analysis in abacus itself. So basically what the tool does is it uses the direct cyclic response, and then it kind of extrapolates, it uses a damage continuum approach, and then kind of extrapolates the variables and then calculates what is the damage initiation and evolution. So it can model progressive damage and failure in bulk in ductile materials, and it can also simulate the delamination at the interface regions. So this is an example of an LGA socket wherein fatigue reliability was studied, like for ball grid, like for BGA joint failure, ball grid array. You can have mechanical loading prior to this thermal cyclic loading, and then use the direct cyclic procedure, see for how many number of cycles you want to repeat the analysis, and then calculate the damage initiation and evolution from that point. And then there is also a technique available in abacus called the submodeling technique, which allows users to study a part of the model in quite detail by including every complexities. So you start off with a global model, do an analysis, and then you take a portion of that model, define all the minor details that you want to consider in the analysis, and then you drive the submodel from the results of your global model. So you can see here that we've got a very good correlation for the LGA sockets. So the FE and the theoretical kind of match, experimental kind of match quite closely. And this is another example of a Gullwing lead. So you can see that damage initiation has started at 199 cycles, and then slowly it started to evolve. So there is damage initiation. So after the direct cyclic analysis, once the stabilized response is reached, abacus then kind of uses the energy calculations for estimating the damage initiation and evolution. So those were the different kinds of analysis one could carry out, like coupled thermal structural or thermal electrical, or you could have thermal structural and electrical. And then you can do fatigue, wear, moisture. So all these kind of analysis can be carried out in abacus. Now when it comes to model building, that is building of the model, like as I mentioned in the beginning, we have tools in abacus for building the model right from scratch. So you can, so abacus CAE is the GUI for building the models. So this is one way of doing it, or you can also get in your models from CAD packages like ProE, CATIA, SolidWorks, and then start building up the model from that. And you have different features and functionalities available in abacus for modeling your structure. So you have geometry import, or you can build the model in the tool itself. You can do patterning. So you have techniques for getting a very patterned kind of a mesh for fracture mechanics studies if you're using the traditional methods like J integral, stress calculations, like stress intensity factors. And in addition to that, one can also customize the whole of the interface to just suit your need. It's not hard-coded that you just have to stick to the interface that the tool provides. You can completely kind of customize it so that you have only a couple of icons, and once you feed in the data and click those icons, your model is ready. So, and just as an example, so this is a kind of customization that was done by one of our offices for creating a PCB modeler. So by using this plugin, all the user has to do is just input few values, and then his PCB will be ready. So this kind of a customization can be very well done in Abacus. And then there are different ways for representing discrete connections. And one way is by using mesh-independent fasteners. So if you want to, kind of connect two plates, let's assuming there is a solder, and which is kind of sandwiched between two plates. So you can either model the solder as it is, or depending on the kind of analysis, you can kind of approximate it and model it as a connection. So mesh-independent fasteners are nothing but simple representations of, say, spot welds, or it could be couplings and things like that. So if you look at in this figure, the attachment points, so you have the attachment points, and then you have different surfaces, and then you have the fasteners which are passing through these attachment points, which will hold all the plates together. And these fasteners which are passing through, they can be the beams or solids. They can be a combination of both solids and beams, or you can also use connectors. So connectors in Abacus are just two-noded elements which can simulate all different kinds of mechanisms like hinge, lock, rotational kind of connectors. So this is an example that I was talking about. So fasteners for solder joints. Imagine you're doing a drop test at a system level and not at a component level. Then it kind of becomes very important that you you make some approximations and then have some components as a representative things. Like for example, in the complete drop test of the assembly of, you can just get away by modeling the solder as a two-noded connection by using connector elements. So in this particular example, bushing type of a connector was used, wherein you can specify the stiffnesses in all the 6 degrees of freedoms. You can define damage, failure, everything. So it acts like a regular solder element, but instead of modeling it as a 3D, you'll just model it as a simple two-noded connection. And then there are also features available in Abacus wherein you can model embedded elements. That is basically reinforcements to the structure. Like a typical example would be concrete in rebars in a concrete, or you have the tire reinforcements. So you can model those reinforcements separately, mesh them separately, and then carry out analysis. And in electronics industry, it would be applicable to PWD modeling with a mesh of copper stacks, and we are separate to board mesh. So you could model all of these white color things that you're seeing here, the VRs. So you could model all of that through reinforcements. And so far we have seen about the different types of analysis one can do and how to build up the model. And so in the next few slides, we'll also see how to carry out reliability analysis. So far we have been talking about a product called Abacus, and we also have a tool called iSight, which can be used for carrying out analysis such as optimization, design for Six Sigma, design of experiments. And it can also be used for carrying out process integration and automation. So you can kind of automate your entire workflow. So here if you see in optimization, typically in a design of experiments or optimization study, you have a set of design variables to start off with, and then you find the optimum design. That is, this is the start point for your initial design, and then you do some kind of approximations to get to an optimized solution. And the red dot which you're seeing here, the big red dot, that is the optimized solution. But if you see, it is very close to the infeasible region. So it cannot be considered as a robust or a reliable design. So we use tools like Six Sigma or Monte Carlo tools to kind of bring that point somewhat inside within the feasible design space so that it satisfies all the constraints and optimization methods. So this is an example, a reliability example in packaging industry. So this is an example we have seen earlier, wherein low cycle direct cyclic analysis was used to carry out a low cycle fatigue analysis for the solder failure. So if you see here, so the N naught here represents the number of cycles to just initiate the damage. And C1 and C2 represent the material parameters, and W is the energy, delta W is the energy. So these are, so N, so one needs to carry out N number of cycles to reach to the damage initiation. So what are the different ways to get to an optimized values of C1 and C2? So one can do optimization studies and can get to an optimized value of C1 and C2. So that is, they can study the design parameters sensitivity, that is, what is the uncertainty in the material by calculating the mean and the standard deviation values. So you have material data from different suppliers. So you can do optimization studies, get to the mean and standard deviation values, and then kind of automate workflow wherein you can simulate the solution, simulate a run for n number of cycles. So in this particular case, it's like 50 jobs. With these two different materials considered. So the idea is to check which one would be more reliable. And then once it goes through the optimization loop, so you have two different optimization loop for two different materials. You collect all of that data and then you kind of do a variable analysis, which is typically used to calculate the fatigue time and also to estimate what is the breaking point in the failure. So this will in turn create an automatic report generation, which will help you to analyze after how many number of cycles will a material do better, or you can basically take a call on which material to use at what number of cycles. So those were some of the reliability based simulations that we have seen by using eyesight. And the next few slides, these are just some references wherein if you see companies like Intel, AMD, and IME, IBM, and Fujitsu, they have been using all these kind of analysis like like for analyzing the creep behavior, for simulating the failure through low cycle fatigue analysis, and they have published quite a few papers in different conferences, in our users conferences as well. So in summary, Simulio is recognized as the brand leader, as the industry leader in electronics industry, wherein one can take advantage of the fast, robust, and compatible solvers that we have, high performance solvers that we have. We have state-of-the-art damage, failure, and fracture mechanics material models. And there are different material models that one could use for simulating things like creep, viscoelasticity. And when it comes to interactions such as contact and all, it can be very easily handled no matter what kind of interaction it is. And it's also a question of ease of use. So we use abacus CAE for building the models right from scratch, or you can customize it. You can make it the way you want. And we kind of provide a unified solution for complete electronics model. So if you have to do a structural analysis and then a heat transfer and then an electrical, you don't have to switch to different tools. You can do it in a single tool called abacus. So wherein the different solvers like standard, explicit, and CFD will help you carry out different kinds of analysis like thermal, structural, creep, fatigue. So even for fatigue, you don't have to move to another tool. You can do it in abacus itself, as long as it's a low cycle fatigue. I was talking about abacus CAE, which is the complete abacus environment. So in CAE, you have different modules for building up your models, like part, property, and then you assemble it, you define loads, boundary conditions. So in the part module is where you can kind of create your own components, be it whatever size they are. Or if it's not the case, then you can get in your models from some other tools like CATIA, depending on which tool. So for some of the standard packages like CATIA, SolidWorks, ProE, and Unigraphics, we have associative interfaces, meaning you develop your model in your CAD package, you just do a click, and then your model gets imported. And if you do any changes, the changes get automatically reflected. So that kind of an associativity is kind of maintained with some of the CAD packages. But if you don't have that, you can bring in your components in a neutral format like STEP or IGS files. you can go from you can do a single component to a whole assembly. You can do the analysis. And whether you're interested in the global analysis, if that is the case, like in the example that I've shown for solder joints, wherein you just take a representative of that by a connection, a two-noded element. So you can go from component to sub-assembly to a full assembly. Basically to give the user an understanding as to what is happening at the background, that is with respect to the solvers, so that if there are any issues, they'll be in a position to debug the model, because it's not that once you submit, you're going to get results. There are going to be issues. So we need to know how to debug those issues as well. So we provide trainings wherein we help you understand what are the different types of errors, warnings that one can possibly get when doing a particular kind of analysis. Like, let's say if you're doing a structural analysis, probably there could be some missing boundary conditions or loads, due to which there would be some convergence issues. So we help the users understand how to fix those kind of convergence issues.
I thank Geetha for a wonderful presentation. I think these tools she has talked about will be of immense use in the electronics manufacturing industry, and I'm sure some of you will be thinking of taking advantage of the technology available.